Here I have a circuit. A portion of the circuit is in a magnetic field. I just want to know what is the magnitude and the direction of the net force on the circuit. All right. So first of all, we just want to find our current. Do this a couple different ways. Our current comes up in this direction, right? It goes through here, and then it goes through here. What is the magnitude of that current? Yeah. Andrew? Yeah, it's just another symbol. Sometimes you can show different cells together. So it would be like two 5-volt cells. Yeah, I'm sorry if that's confusing, but it's just a 10-volt battery. But what is the current? Right, from Ohm's law, I is equal to V over R. That is 10 over 5, 10 volts for 5 ohms. So I have 2 amps going through this this wire. You could use the right-hand rule, or you could just you could say that L, the vector L, is the vector from here to here. It has a magnitude of what? That vector L. This is the length of the wire. 10 centimeters, or I would express that in meters, so 0.1 meters. What is the direction for L? It's down, negative J direction, so negative 0.1 J. And then the magnetic field in vector notation is what? Right, well, I see. The magnetic field is 2 Tesla. All right, so it's going to be plus 2I. And then it's just a matter of doing the cross product. We have everything. It's pretty simple cross product. IL cross B. That's going to be 2 amps times negative 0.1 meters in the J direction, crossed with...
Why is B2I and B is going into the page?
Oh, it's not supposed to be into the page. Why does it say B in there? That was just a mistake. I'm sorry.
It said the problem says 2 Teslas pointing into the page.
Yeah, that's a mistake. The magnetic field is shown to the right. I'm sorry. All right. And now, so the magnetic field is plus 2I, cross plus 2I, and then that's going to be negative 4 times 0.1, that's negative 0.4 J cross I, which is going to be 0.4 K. 0.4 newtons in the K direction. You can use your right-hand rule, J cross I. This is I, J, K, and J cross I equals negative K. All right. Another way you could do that is you could just say, you might find this a little simpler, F equals ILD sine theta. Just to find the magnitude of that, that's going to be 2 times 0.1 times 2 Tesla, 2 amps, 0.1 meters, 2 Tesla, and you get 0.4 newtons. And then you can just use your right-hand rule. We have our vector L is down, our vector B is to the right, and then we do the right-hand rule like this. It's out of the page. The vector F is out of the page, which is what we've got down here. It's 0.4K, which is out of the page. Might find that a little simpler. All right. Several cross products in this chapter. You will see the cross products on the test, but on this one you didn't have to do the cross product. No. Okay with this?
What's that?
What's what?
What's that?
0.4 K. 0.4 K. All right. Let's try this next one, and we'll move into electric motors soon. Can I go down from here? All right, so let's say we have this loop of wire. This loop of wire runs into the page on this side and out of the page on this side. And it's allowed to rotate about this axis right here. It's kind of like the motor that I showed you last time. You had a loop of wire and a magnetic field. But here, what direction does this loop turn? At least initially, what direction does it turn? You just want to take one side. Remembering too that the magnetic field runs from which pole to which pole on a magnet. Okay, yeah, north to south. So my magnetic field runs in this direction. And you can just take one side and ask yourself, what is the force on that wire? So take the right side or the left side, doesn't really matter. All right, about 10 more seconds. Stop at 2 minutes. That's everybody. Okay, very good. A is the right answer. So we just want to pick one side of this. So I'll take, for example, this side. I have a current that is into the page and a magnetic field that is to the right. And so my force is going to be down. So if I have a force that's acting downward on this side, it's going to pull the loop down. And you can do a similar thing and find that the force on this side is in the upward direction. So my whole loop is going to turn like this. It'll turn in that direction. Now what happens when this loop turns 180 degrees? What happens to those forces? Now think about it, if you turn this thing 180 degrees, you flip it over, and now this side is going to be over here. So instead of the current going into the page, this side will be over here, the current will be coming out of the page. So what's going to happen to the forces on the loop? They're going to switch. So whereas before you had your forces causing it in a clockwise rotation, when it turns 180 degrees, the forces are going to switch, and it's going to go back the other direction. Right, so they're going to flop every time you go 180 degrees. So if you just have a regular DC motor with no other alterations to it, your loop is just going to flop back and forth like that. There are a couple of different ways to get over that. So as the loop rotates, the force changes direction. When it's rotated 180 degrees, the force changes direction. That's kind of redundant. So it goes the opposite direction. So in electric motors, you have to change the direction of the current after each revolution to keep the loop rotating in one direction. Couple ways to do this. Can I go on down from here? I'll show you an animation in just a second. The first way to do this is to use a type of switch. It changes the direction of the current. Y'all use a switch in lab, right, to change the direction of the current. What was that called? Y'all remember? No, double pole, double throw switch. This is similar. It's not called that. They call them brushes. If you've ever dealt with electric motors, you might have heard talk of these. That's a BRUSH. And these are used in DC motors, direct current motors. We've been dealing with direct current. Basically, if you were to plot the current versus time, I versus T for a DC motor, the current would always be constant. It would never change, right? And it's always going to be in one direction. All right. I have a little video to show you. I think I actually have a couple. Let me see. Can I come away here? Yeah, maybe so. I don't know. Anyway, the other way to do this is to use AC electricity. That's alternating current. If you plot out the AC electricity, the current versus time, it's going to oscillate back and forth between some positive current and some negative current. And this is what we use in our homes. It oscillates at a very regular frequency. So, for example, in the United States, you might know the frequency of our AC electricity. You might have seen this on your electric devices. No, it's 60 hertz. So if you look on your electric devices, often you'll see a frequency that they're optimized for, and in different countries it's different. But in the U.S. we use 60 hertz.
Because you have it on your power supply on your computer.
Yeah, there are multiple things there because you have the power rating, the voltage, the current, and then also sometimes you see the frequency, not always. All right. Now, so with an electric motor, you run a current through a wire in a magnetic field, and it produces a force. What happens if you take a wire and you push it through a magnetic field? What happens in the wire? Right, you get current that flows. We've already seen this, right, where we pushed a wire through a magnetic field, such as this one. If I have a wire that I'm pushing through this magnetic field, it will generate a current. I like to think of it as I have this wire. It's like this tube, and then there are these positive charges within it. And if I push them through this magnetic field, I can, through our right-hand rule, figure out that I'm pushing them with a velocity in that direction, and so they're going to feel a force that's upward. So in this wire, I will have a current that flows upward. Remember here also that I'm assuming a conventional current, so that I'm assuming the flow of positive charges. So whenever we talk about the flow of electricity, we're talking about the flow of positive charges. So the direction of the current is up or down? Right. So a generator works the same way as this. It's just like an electric motor, it's just the reverse. All right. I'm going to go get something in just a second. I have something I want to show you first. But, or no, I'll just bring it on Monday. Sorry, I forgot to bring it today. Let me make myself a note. Now, have y'all used a mass spectrometer before? Yeah. I mean, if you haven't yet, you will if you're a chemist. So a mass spectrometer is an instrument that we use to select out particles that are unknown when we based on their mass, not only their mass, but their mass to charge ratio. And we do that by moving a stream of particles, these unknown particles, into a magnetic field and measuring the radius at which they curve through that field. So, for example, let's say that we have a charge here. Let's say that this is a negative charge, because then it goes in the right direction. If I have a negative charge moving here, it moves to the right with a magnetic field that is into the page. And so if it were positive, it would feel a force that was up. But if it's negative, it feels a force that is down. Remember, if you have a negative particle, you get the opposite of what you find. So here I have a velocity and a force that are perpendicular to one another. We call this type of force what? When it's perpendicular to the velocity? We said this previously, but what specific type of force is this? A centripetal force, right. So this is a centripetal force. It's perpendicular to the velocity vector, and it's going to cause the charge to move in a circular pattern. Rob?
If it was pointing this way, and the beam is going into the page, the force is going up, so would you have to change the so it was going this way?
What now?
you have V pointing in the positive direction.
Right.
So if you got E going into the page, velocity is going this way, force is going out.
Yeah, I'm sorry. I made it a negative particle.
So you should change the V going the opposite way.
Mm-mm.
But how is it going to be up, be down, or be? How's the force?
Remember, if your charge is negative, you take the opposite of your right hand rule. So here, my V is in that direction. Magnetic field is into the page. So you're right. The force would be up, except that this is a negative particle, and so that makes the force opposite of what you find.
I figured that it would be just easier to draw velocity with a force or velocity vector the other way.
You could do that, yeah. And then it would, if you had a positive particle moving in this direction, it would feel a downward force. That's what you're saying?
Yeah,
That's correct.
So you just got to remember if you got a negative, just
Right. So anytime you encounter a negative particle, an electron or whatever, just take the opposite. Is it?
So you would just assume this is the negative direction of whatever, which one you're finding path B or V?
Right. Yeah, no matter what you're finding, just find it by the right-hand rule and then take the opposite of it. Take the opposite of what you're finding. So it's a fairly simple thing. Now we can write our force like this. F is equal to QVB if theta is equal to 90 degrees, which in a mass spectrometer it is. You set it up that way. And then the magnetic force is a centripetal force. So you can equate that then to the mass times the centripetal acceleration. If you recall this from last semester, that QVB equals mv squared over r. And then from this we can get the cyclotron equation. So if I solve this for r, let's see, one of my v's cancels there, and r equals mv over qv. It's called the cyclotron equation. It's on your equation sheet, or at least some variation of it. And so when you have a mass spectrometer, you give the particles a certain velocity, you have them in a certain magnetic field, and you measure r, and then you can find, through these measurements, the mass-to-charge ratio. And given the mass-to-charge ratio, you can select out those unknown particles based on what you know particles have, or their mass-to-charge ratio. Let's do an example. So say, for example, I have this scenario. I have a particle with this speed and a magnetic field, and then it has a radius of about 16 centimeters, or 0.16 meters. So I can calculate then what is the particle, the mass-to-charge ratio. Let's see, what is it? R equals mv over qv. So the mass-to-charge ratio is rb over v. That's r is 0.16. V is 0.35. Divided by V, which is 1.79 times 10 to the 6th. Generally, the way you accelerate these particles is you put them in an electric field, and depending on the length of the electric field, you can accelerate them to a known velocity. All right, and so if we calculate that, let's see, I think it's like, I don't know what this is, 1.04 or something, is that right?
It's
Tritium? I have 3.13 times 10 to the 8th. This is in kilograms over coulombs, because it's a mass-to-charge ratio. And then you just go through here. Oh, look, I've already calculated it for you. So it's right there, 3.13 times 10 to the 8th, based on what we know about these. So, all right. Oh, yeah, it should be -8 right here. I'm sorry. All right, so mass spectrometer is pretty simple. I have a quick little video here just about how a mass spectrometer works. You take your sample, you vaporize it, you put it in an electric field to accelerate it, and then you So, yeah, my wife and I, we submitted 3 grants. We got all 3. That was exciting. She got $20,000 just to buy a telescope for crying out loud. That's pretty good. State government.
Remember, stop with it.
Oh shoot, I was saying that.
Jumping for joy.
Alright, so mass spectrometer is pretty simple, but it's very powerful to pick out unknown particles. Let's try this quick test. Just like we did before, you just want to calculate the mass-charge ratio for the particle in the mass spectrometer, and then determine from this list what is the particle. Talk really, really fast. No, if we don't finish today, we'll finish it Monday. The next chapter is just a one-day chapter. This is a very famous experiment in the 20th century to determine the mass-charge ratio of an electron. They did this basically. Let's try to wrap it up by 10 or 15 seconds.
What kind of paper should we wrap it up with?
For 325. 5 more seconds. Okay, very good. Hydrogen is right. I start with my cyclotron equation. R equals mv over qv. Solve for m over q, which is r b, what's it, rb over v? rb over v? Right, okay, and put in the values. Here's r, here's b, here's v. I think we get like 1.04 times 10 to the -8. Alright, and that's going to be our mass charge for hydrogen. You can look through, and that's the only one that will give you a 1.67 over 1.6 is basically 1. Alright, so hydrogen is the right answer. You can see a free response like that in the test. It's a fairly simple problem, but it's an important problem nonetheless. Okay, have one more application of the right-hand rule, and it's called the curl rule in this case. The idea being that a current in a wire creates a magnetic field that surrounds the wire. This was discovered back in the 1700s by a number of folks. And to find the direction of this magnetic field, we use the right-hand rule. In particular, this is called the curl rule. So this is a different application. We let the thumb of your right hand go in the direction of the current. And then your fingers wrap around to get the direction of the magnetic field. So if I have a wire, say this is a wire, and I have a current that's going in this direction, the magnetic field goes all the way around this wire, all throughout space. And I can find the direction of it by letting my thumb go in the direction of the current, and then my fingers wrap around. So over here it's going up and down, up and down. It rotates around like that. All right? So if I have a wire like this, on the left-hand side, it's going to be going into or out of the page. That is over here. That's right, it's going out of the page, and then on the right-hand side, it'll be going into the page. We can draw our wires in different ways. So, for example, I can also have a wire that's coming out of the page like this. So I use the dot symbol to represent that. And then the magnetic field will go clockwise or counterclockwise? Right, counterclockwise. Like this. I let my thumb go in the direction of I, and then my fingers fold around like this. Now at any one point, the magnetic field is going to be tangent to that circle. So if I pick a point, say right here, the magnetic field will be in that direction. Right here, the magnetic field is in that direction. Here, it's in that direction. It's always tangent to the circle. All right? That's okay. Did I tell y'all what I did in my other class? That I was part of this psychology experiment? Did I tell y'all about this? Well, Jonathan DeRocher, who is in psychology, I think he's a grad student or something, he was doing an experiment about what is the effect of cell phone policies in classes. So like if you have a written cell phone policy, which I do not, but if you have a written cell phone policy, how does that affect the student's usage of cell phones? And he had me set up the cell phone policy in my syllabus, which I don't usually have because, you know, y'all are adults, whatever. And, but had me write a cell phone policy saying they're strictly forbidden. You may not use cell phones in class at all. And then on the first day of class, I'm supposed to read the cell phone policy to the students and explain it to them and tell them, you may not use cell phones in this class. But then during class, I was supposed to get a call on my cell phone, right? And then, so how would this affect the students? And of course, I don't have a cell phone. We sort of have one, right? My mother-in-law has a cell phone. She gave it to us. We've been through all this. And so I had the cell phone. I don't know how to use the damn thing, right? So yeah, something was wrong. It wasn't working right. He was supposed to call me during the middle of class, but then he didn't call me because I didn't turn it on. I don't know, whatever. Something was wrong. But then the thing starts beeping at me, and so I pull it. I'm like, what's going on with this thing in the middle of class? And it was beeping. I couldn't turn it off. And so it made the point to the students that, you know, I had a cell phone. I was using it in class and stuff, which was the point. But that's the second.
Question about this one here.
Yeah.
If you go back to page 203, using this rule right here, so it only works on straight wires. So if that wire was square, like that.
No, we'll see that. It'll work on a loop too.
Okay, so like say 203, go back to page 203.
This one right here? Yeah. We're going to get to this.
One more.
Oh.
The one with the magnet, the wires inside the magnet, it's looping.
This one?
Yeah, I think it's farther down.
Up or down?
It's right after that one you just showed.
Right here? This one?
Keep going. It's the one, 206. Look at 206.
Oh yeah, so
current was going, if you're looking at the right side, the current's going in,
Mm-hmm.
go up this way.
It's going to generate its own magnetic field, right? In fact, that's where that force arises, is because the current generates a magnetic field, and it interacts with another magnetic field, and that actually what causes the force.
So you could look at the way the axis goes, you gotta look at the current.
Yeah, it's easier just to look at the current. But you can use the curl rule to find the magnetic field generated by a coil of wire. We'll see that with solenoid switches in just a second, with solenoids. In fact, y'all should have done that with in your lab when you did the tangent galvanometer, because you had to know the direction of the magnetic field generated by the tangent galvanometer so that you would know how to align it with the Earth's magnetic field. Y'all do that? So remember? All right. All right, let's look at this. We can find the magnitude of this magnetic field. This is in your equation sheet, but make sure that you're aware that it's there and how to use it. It's equal to mu naught I over 2 pi r. So if I have a wire right here, the magnetic field is into the page on this side and out of the page on this side. If this distance is r, I can calculate the magnitude of this. It's just going to be the permeability of free space, that's this 4 pi times 10 to the minus 7, times the current over 2 pi times r, where r is just that distance from the wire. Again, that's in your equation sheet. You could see it next Friday. Just make sure that you're aware that it's there and how to use it. There's some homework problems too. Also note that this magnetic field does extend all the way out into space. So that magnetic field will get smaller as you go out, but it extends all the way out to the ends of space, basically. All right. Let's do this quick test. Here I have a point A that's the same distance from these two wires. What is the magnetic field due to the two wires at that point A? And in the two wires, on one of them, you have a current that goes up, and on the other, you have a current that goes down. So then what is the direction of the magnetic field due to, or at that point A, due to those two wires? In, out, left, right, or no magnetic field? Right-hand side, the magnetic field will look like this. What does it look like on the left-hand side? And then how do those add up? All right, so a few more seconds. Stop at 128. All right, we're sort of all over the page here. So let's see. On the right-hand side, what does it look like to the left of the wire? For this, the red wire that I have here, over here on the left-hand side, you can't see that. But right here, what does it look like? Into or out of the page? That's into the page, right? And on the right-hand side, it's what? Out of the page, right? Now, at the point A, I have two magnetic field vectors. I have this magnetic field vector, and then I also have this magnetic field vector. And they're going to be equal in magnitude, right? Because they're equidistant from those two wires. So what's going to be the net magnetic field there? Into or out of the page? It's going to be out of the page, because I have these two vectors that are both pointing out of the page. All right, so B is the right answer there. Let me show you a couple things. Now, if the wires are going in opposite directions, or in the same direction rather, so let's say that I have a wire going in this direction, and a wire with a current going in this direction. On this one on the right, it would be into the page and out of the page. And the one on the left, it would be into the page, out of the page like that. So at a point in between, what would be the magnetic field? It would be 0, right? Because those two vectors would cancel out. Right? What about, let's go back to this situation right here. What about at a point over here? What is the direction of the magnetic field? Huh? It would be into the phase, yeah. But remember, you do have two vectors that are applied here, because I have a vector over here due to the blue wire, and then I also have the vector due to the red wire. So why don't they cancel out, those two magnetic field vectors? Right. The blue wire is further away, so the magnitude of that magnetic field is smaller. All right? Let's try this one. I'm going to go and start. I'm going to show you how to do it on the first one. They're kind of tedious, these things, because you got to do sort of directions of magnetic fields for about 6 different wires. All right, so here I have 4 configurations of wires, and I want to know what is the net magnetic field at point P. So I'm going to first take this wire right here, and it has a magnetic field that goes around in this direction, counterclockwise. So at the point P, the magnetic field points in that direction.
Where did you get this?
Well, the wire's a dot. It's like it's coming out at you, right? As opposed to an X. Here, I have a magnetic field that's in that direction. Our wire in that direction, so my magnetic field looks like that. So at point P, the magnetic field looks like that. Here, still counterclockwise. So here, the magnetic field looks like that. Here's the blue right here, counterclockwise. So what is the net magnetic field for A configuration? Right, it's going to be 0. I'm equidistant from all those wires, so the magnitudes of their magnetic fields are all the same. So my magnetic field is 0. I'll try B and C on your own.
We're supposed to. We're supposed to.
Yeah. But go ahead and try B and C on your own, and then figure out from their sum of the vectors which has the greater magnetic field.
Okay, I don't understand. You want us to put the answer for the first one, or?
Well, I was just showing you the first one. So A is not the answer, because it has a 0 magnetic field. Unless they're all 0, but they're not. So you'll find one that has a greater magnetic field that's non-zero. Try to wrap it up. 10 or so seconds. I'll stop at 3:45. 3:45. Okay, very good. B is the right answer. With C, you find the magnetic field is what? 0, yeah. So they all point in opposite directions, just like A. I'll leave you to do that on your own, but I'll go through B in case you don't get it. So with this one, my magnetic field is in that direction. And so at point P, it's like that. With this one, it's in that direction. So it's in there at point P. This one, clockwise. So it's in that direction. And for this one, down in the far right corner, it's clockwise as well. Wait, no, that's not right.
No, because
It's counterclockwise, I'm sorry. Counterclockwise. And so it's like that. So I get 4 vectors that look like this, and so the net vector is in that direction. See a similar question on the concept test next time. But one more small thing. We have a few more minutes. I'm going to skip this magnetic force between 2 parallel conductors. It's sort of more of the same. But I do want to show you solenoid switches. So all this business, get rid of. If you have a current loop, you can generate a magnetic field. And the magnetic field of that current loop, this is just like you had in the lab, where you had this loop of wire with a current going through it. The magnetic field is equal to mu naught I over 2R. Again, this is on your equation sheet, but be careful because this looks a lot like the equation for the magnetic field due to a long straight wire. So just be careful with that you know what they are. They come in order of this, so if that helps you. Mu naught I over 2R. If you have multiple turns of wire, you just multiply it by N. It increases your magnetic field. Remember in the lab, you had different number of turns of wire, and then you use different currents. If you increase the current, you increase the magnetic field. If you increase N, you increase the magnetic field. We can also find the direction of the magnetic field with our right-hand rule, the curl rule. Let our fingers go in the direction of the current, and then they wrap around, our thumb go in the direction of the current rather, and then they go into the page and out of the page over here. If you do that all the way around, you find that the magnetic field is into the page in the center, and it's out of the page all the way around. If you flip the direction of the current, it flips the direction of the magnetic field. We use this for a solenoid switch, the idea of a current loop. Next time we'll watch a video, but let me just show you a picture right quick. In a solenoid, you just have a current running through a magnetic field, and in a solenoid switch, you'll put a little magnet or a piece of steel inside that magnet, that coil of wire, and when you turn on the magnetic field, it will cause this piece of magnet to either go out or it'll pull it back in. Next time we'll watch a little video about a solenoid switch. But where do you see solenoid switches? Or you don't see them, but where do you, does anybody know where you commonly use a solenoid switch? Where? Okay. It's very useful to do something mechanical from a distance, right? Anytime you want to, but on your car you have a solenoid switch as far as your starter. So I don't know if modern cars have this, but older cars did. You actually, on your starter motor, you had a separate little thing that was called the solenoid, and that was just this. It was a switch. So when you turn your ignition, it would engage the switch and start the starter motor.
Can you go back?
Yeah.
To make a railgun.
We have a little bit more left. Yeah, this is also the idea behind a railgun.
I should make one.
We do have a little bit more, but on Monday we will finish this. We just have the concept test really. I'm going to show you this British guy with a solenoid switch, and then we will go on with chapter 6. So please, if you haven't watched those screencasts, go ahead and do that. It's only about 20-25 minutes worth. Go ahead and do that, and you will be responsible for that. But then we'll carry on. But you'll need to have watched that before we carry on Monday. All right? Have a great weekend.
Let's make a railgun.
Hmm?
Let's make a railgun.
Okay.
With
PVC
Spider
heights.
It's fairly expensive.